Hi, and welcome back to this last video in our series on the Fourier uncertainty principle. Sorry, I'm just moving windows around. Okay, so welcome back. And we've already proved Tau's uncertainty principle in the last video, and sorry, in the previous video, and in this last one, we're going to apply it to prove the Cauchy-Davenport theorem, just to show that we can actually do something with this theorem. Okay. So it's not going to be very difficult to prove today, but we're going to have to make some definitions. Actually, well, I should restate what the Tau's uncertainty principle says, right? So let's just scroll up a bit. So we've shown that this Tau's uncertainty principle, it's for it's over ZP, where P is prime and ZP is a cyclic group. And it says that if f is a non-zero function on ZP, then the size of the support of f plus the size of the support of f hat has to be at least p plus 1. But conversely, if a and b are non-empty subsets such that their sizes satisfy this inequality, then there's some function f whose support is a and whose Fourier transform has support equal to b. And we're going to use actually both of these directions, both this inequality and sort of its converse, in the proof of Cauchy-Davenport, of the Cauchy-Davenport theorem. But first, we're going to have to define stuff that we didn't define in the earlier because we didn't need them, but we will need them now. So let's define here. So definition, the convolution f star g of f, f and g are both from some abelian group Z to the complex numbers, is given by so f star g. It's going to be a function. So let's just write here f star g is going to be a function from Z to the complex numbers as well. And so for some x in Z, it's going to be equal to the expectation over all y plus z equals x, f of y, g of z. Okay? So we need, it's a sum over all pairs y and z that sum up to x, and then you apply f to y and apply g to z, and you sum them all. Okay, so the reason the convolutions are kind of cool in Fourier analysis is because they actually behave quite well under Fourier transform, and that's what this theorem says. But I don't know what behave well means, but like they're kind of nice to think about under Fourier transform because of this convolution law, which says that, so let Z be it's going to be a finite abelian group because we're just considering that, and f, g are functions from Z to C. Then for all, so I guess then for all chi in Z hat, so the dual group obviously, we have the Fourier transform of f convolution product with g evaluated at chi is equal to f hat evaluated at chi, g hat evaluated at chi. Okay, so the convolution of the Fourier transform. Oh, someone's calling me. That's never happened. Okay, so that was ever so slightly infuriating. It was like a one of those, I don't know, robot calling things. Okay. So where were we? Yeah, so I said the Fourier transform of a convolution product is the product, like multiplication, of the Fourier transforms. Okay, and let's just prove that. It's not so hard. So proof. So we expand. So the Fourier transform of f hat g is, of course, going to be the expectation of all x in Z. Yeah, so of chi, yeah. of f star g of x, and then chi of x. Okay, and then now we expand out the convolution part, so this stays the same, and then now we have expectation of all y plus z equals x, f star g of, oh sorry, I just copied that, that's not what we want, f of y, g of z. But remember, this is actually, since x is y plus z, we can actually write this chi of y times chi of z, because chi is a character, so it's a homomorphism, but all of this is barred. Okay, and now x no longer actually shows up in here. Okay, so we can actually just get rid of this x part and take the sum over all y and z, because y plus z is going to be x for some x and z. So this is expectation of y and z, expectation of z and z, f of y, chi of y bar, and then g of z, chi of z bar. And now we see that this is exactly f hat of chi, g hat of chi. Okay, so that's pretty easy. So that's the convolution law. All right, so now we'll define something else. So definition. So let A and B be subsets of a finite abelian group Z. Okay, the sumset A plus B, it's also going to be a subset of Z, is A plus B equals set of all little a plus little b, where little a is in big A and little b is in big B. Okay? So it's really exactly what you thought it was. And this is related to convolution, so just note, if the support of f is equal to A and the support of G is equal to B, then the support, of f star G is, well, it's not equal to, but it's a subset of A plus B, right? And that's clear because, look, when we defined f star G, we only took a sum over all y plus z equals x. So x has to be in the sumset of A plus, the sumset A plus B, for this not to be 0. If we took x outside of the sumset, then all of these, either one of these would be 0, so the whole product would be 0. Like at every term, one of the factors would be 0, right? So the support of f star G is a subset of A plus B. And then the convolution law shows us that the support of f star G hat, okay, is equal to A intersection B. Okay, and that should be clear as well. Sorry, not A intersection B. It's the support of f hat. We didn't give names. Support of f hat, intersection of the support of G hat. And the reason is because, well, if you look at this, okay, so if chi is in the support here, then this product has to be non-zero, meaning that both of these have to be non-zero. Conversely, if both of these are non-zero, then this is non-zero, right? Okay. So that's that. That's the link between sumsets and the convolution product. And so now we're able to state and prove the Cauchy-Davenport theorem. So theorem, Cauchy-Davenport. So Cauchy is, I think his name's like Louis Augustin or something like that, and Davenport is Harold Davenport. But it's funny because Cauchy died Cauchy died in 1857, and Davenport was born in 1907. So I always imagine whenever I see Cauchy Davenport, I imagine like the ghost of Cauchy, like looking all blue, like Obi-Wan Kenobi, helping Davenport do his proof. But I think what actually happened in real life is Cauchy proved it 100 years before Davenport, and then Davenport just didn't see it and proved it independently. That's how it usually is with these things. So it says let A and B be non-empty subsets of the cyclic group prime order. Then the size of A plus B is at least the minimum of these two quantities, A plus B minus 1 and P. Okay, so it's giving a lower bound on the size of a sumset. All right, so proof. Okay, so there's a lot of like counting in here. It's kind of you know, it might be hard to wrap your head around, but we'll just go slowly. So since A is non-empty, we can choose a non-empty set X in ZP, contained in ZP, sorry, is an X, with P plus 1 minus A elements. Okay, so it's never empty because X is not empty because if A was the whole group, there would still be, so if A was P, there would still be one element in X, and also, yeah, X can't be too big because A is not empty, so the biggest X can be is all of ZP. Okay, so ZP minus X has size of A minus 1 elements. Okay, so that's going to come in handy later. Now, since B is non-empty, if the size of X plus 1 is greater than the size of B, we can pick a non-empty Y prime inside X with size of X plus 1 minus B elements. So it's the same process, except now it's just within X. And then let Y equal Y prime union ZP minus X. Okay? So, so the size of Y, let's count the size of Y. So we have, it's this Y prime. Okay, so here, I'll just write out the thing. So it's P plus 1 minus size of A plus 1 minus size of B plus A minus 1. But what is all this? So this part here, so what's A? Sorry, this part here, that's X. Okay. So then this part here is Y prime. And this part here is ZP minus X. Okay, so that's the size of Y, and they're disjoint, so we add it all together, right? Okay, well, these two are disjoint, sorry. Okay, so that's the size of Y in the first case, but in the second case, so if this was, if X was too small, so otherwise, sorry, let's just write, if instead we have this size of X plus 1 is less than or equal to B, then let Y prime be any singleton subset of X. So this looks like X prime, but really it's X. Okay. I know what X prime is. And since P minus X is going to be greater than or equal to p plus 1 minus size of b, that just comes from this inequality here. What can we do? We can find a y prime prime in zp minus x, so this is set minus x, by in I mean subset of, such that, so not nice, with size p minus b. Okay, well, we can throw out that one. Okay, so now we let y equals y prime union y prime prime. Okay, so we again have size of, we never actually cancel things out. Let's just write this here. The p's cancel. Is there p's? Okay, so there's a p. Okay, let's just use red. These cancel out. This cancels with that. So it's p plus 1 minus b, right? And here we again have p minus b plus 1. So size of y is equal to p plus 1 minus b. And in both cases, like we kind of combine both cases. And in both cases, we have x intersection y. Okay, so in the first case, so it's max. In the first case, it's size of x plus 1 minus size of b. And in the second case, it's just 1, like a singleton subset, right? The intersection is y prime in both cases. So that's what we're counting here. And we can rewrite this. So since x is p plus 1 minus size of a, so it's p plus 2 minus size of a minus b. Okay. So we've constructed, this has been really annoying and, all sorts of little details and a couple cases. What have we done so far? We've done, we've taken a, we've taken b, and we've constructed a set x with p plus 1 minus size of a elements. We've constructed a y with p plus 1 minus size of b elements, and the intersection has this size. Okay, that's all we need to know for going on. Okay, by Tau's uncertainty principle, okay, since the size of a plus the size of x is equal to p plus 1, and the size of b plus the size of y is equal to p plus 1, okay, we can find f with support of f equals a, and support of f hat equals x. And likewise, okay, we can find g with support of g equals b, and the support of g hat equals y. Okay? And we saw before that the support of f star g is a subset of a plus b, and the support of f star g hat is equal to x intersection y. Okay, so a plus b, size of a plus b, sorry, plus the size of x intersection y. This is going to be less, sorry, at least, because a plus b is a superset, it's going to be at least the size of the support of f star g, so f star g's zeroth norm, plus f star g hat zeroth norm, right? But by Tau's uncertainty principle, again, like we're using the other direction now, we know that this is at least p plus 1. Okay? And so, hence, we have a plus b is greater than or equal to p plus 1. Now you subtract off this x intersection y, which is max of p plus 2 minus size of a minus size of b, 1. And this is equal to the minimum, right? We're subtracting a maximum. So it's going to be a minimum of p plus 1 minus that, which is going to be a plus b minus 1, and p plus 1 minus 1, which is just p. Okay, that's exactly what we wanted, right? Okay, so that's the Cauchy-Davenport theorem. We've actually proved the Cauchy-Davenport theorem before on this channel in a video. I think that came out in it's like almost 2 years ago now. Start of 2021, I think March of 2021, called the combinatorial Nullstellensatz. And so in that video, we used the combinatorial Nullstellensatz to prove the Cauchy-Davenport theorem, I believe. So this is actually the second time the Cauchy-Davenport has shown up on this channel. But here we gave a Fourier-algebraic proof, in quotes, because I don't know if that's not really a branch of math, but it's got Fourier analysis, it's got algebra, it's a Fourier-algebraic proof of the Cauchy-Davenport theorem. Okay, and with that, thank you for watching, and thank you for following this series on the discrete Fourier uncertainty principle, which has now come to an end. Okay, so see you next time.